Collin Mamdoo has joined us. And Collin has been a dear friend of this program ever since its inception. And so, Collin, thank you very much. Collin comes from a strong background in communications and connectivity. He was just mentioning to me that he's moved on from Vodacom, where he was for a considerable period of time and held a senior position in Vodacom in South Africa. And Collin, I believe from our previous conversations that you are actually studying towards your PhD at the moment. And how is that going? Is it done? Do we refer to you as doctor?
Not just yet. I certainly will invite you to the party, but yeah, still working on it.
Okay, absolutely. And that is really, a massive challenge, because when we get to that point of our education, we're completely alone. It's completely up to us. And that's when our self-discipline is really, really tested, and it's one of the things that we've been stressing with the participants on this program, is that, it's all around you get as much out of the program as you bring to the program. Every single one of the assignments is really valuable and actually really interesting. So, do them or don't do them. There's no consequences. If you don't, there can only be excellent consequences in terms of following on with like mission 2, etc. with Intelsat. So, Collin, thank you very much for joining us and taking us through power considerations. It certainly is. It's something that we have to consider when we do our group assignments, which is the design philosophy behind a satellite in orbit that would be assisting with solving one of the Sustainable Development Goals. Because the thing is, that's what we find is that, power budget, whatever you choose as your payload, is going to consume power. Your processor, however much you need to be processing on board, is going to be consuming power. And, it's one thing to say, well, we're just going to put on more solar panels. Generating power also creates heat. And when you're in a vacuum, you can't just turn on a fan to get rid of that heat. So working with and really understanding power itself, and how that links to communication and connectivity, because they intrinsically bounded together. And just, final bit of my introduction is that what we found is that when anybody has a challenge connecting their kit to the Wi-Fi, it's because of power, distance, signal strength. So it's all related. So I think with that, I'd like to hand over to you, Collin. Grace and I are going to be monitoring questions and things like that. So yeah, if we can hand over to you at this point.
Excellent. Thank you so much for that wonderful introduction, Judy. Yeah, it's been a while that I've been away from the program, but great to be back on again. And then just a quick comment on the PhD as well. I think for the benefit of the participants, the thing about PhD is, like, I believe that every single one of you right now are actually doing your PhD, because at its core, right, your PhD is really about experimentation. It's about developing a hypothesis. It's about testing. Some of the work I think you've already done with Judy and the team, especially when it comes to Kibana, for example, is looking at the data, trying to find patterns within it, summarizing it using statistics, things like that. Those are all elements that would absolutely lead you on to even complete your own academic careers. So I think there's certainly potential for each and every one of you to continue on that path. But I think, for me, to this particular topic, I really enjoy because power is currently a topical issue, whether it is in South Africa or in Kenya or in Rwanda. We all understand that there are some power issues. I'm just sort of, as I mentioned, Kenya. I do know that there are some political events that potentially might be the reason why some participants may not be joining. But yeah, I mean, we do hope that everything goes well and everyone is safe ultimately. So with that complete, I just quickly want to bring up my presentation and then we can jump straight into this. I think that's the one there. Okay. I'm going to quickly run into presentation mode. Judy, can you confirm that you can see that in full screen?
Yes, it's perfect. Thank you.
Okay,
Perfect. Thanks,
fantastic.
Collin.
Great stuff. So, the thing about I want to sort of start off by telling two little stories, and while I'm going through these two stories, I'd like for anybody to quickly in the chat group, you're welcome to quickly write down what am I talking about? What do these two stories have in common? You also at any point during the presentation, what I'd like to deliver here is or facilitate is a conversation. At any point, please just unmute yourself and talk. So we would love to hear you share your comments. Don't feel shy whatsoever. If you feel you're interrupting, you're not. We're all just having a great conversation about space and power. So the picture on the left-hand side, some of you may have seen this in the movies, but it's a movie about Apollo, and specifically Apollo 13. And there was a very specific disaster that struck Apollo. But more specifically, you'll find that the oxygen tanks were actually affected, and the oxygen tanks also ran some of the fuel cells. And ultimately, what happened was there was an issue around a lot of the equipment shutting down. So what a lot of the crew eventually did is you'll find the module sort of stuck at the right-hand side of that Apollo 13 command module is the lunar module, right? So that's essentially the module that was actually called Aquarius, I think. Aquarius, however, did have power available. So what actually happened was that the crew ran into Aquarius. Aquarius, however, did not have any thermal protection. So of course they couldn't use Aquarius to re-enter Earth for that matter. But it had power and it could support the basic your life support systems. However, it was terribly, terribly cold. As you can imagine, in space, that's the issue. But as the entire Apollo 13 approached Earth, and just hours before they landed, they quickly ran across back into the main module, started up all the equipment again, and had just enough power to make it through and land on Earth. The second story on the right-hand side is what a resilient little fellow. So people at NASA call this little guy Opportunity. And Opportunity is essentially a rover that's designed and spent time in Mars. So they used these rovers to basically get around, etc. Now, Opportunity was actually designed to operate for what I believe was 90 days. But over time, if you look at the history, you'll find that Opportunity operated for 15 years. They found that there was quite a lot of wins now and then that they picked up. And also they tweaked a lot of the power management, etc., on board to help it reach that sort of lifespan. So very quickly, does anybody have a clue? You're welcome to just shout out the answers or type it into the text boxes. Well, what do these two stories have in common, and what are we really talking about? Or you could just share your general comments. What did you think about those stories? I see there's a message in the chat group. I see Josh popped a message. Is it ARE? Does ARE stand for a particular abbreviation? Does it expand to anything, Josh? Oh, okay. Sorry, it was just an incomplete sentence. Okay, so are they about resilience? Yes, I guess resilience, but a little bit more about that. Resilience in terms of what? Yes, David, I think you're certainly onto something. It's definitely around power. Judy says, in the case of Mars River, could they change the power management by uploading new code? Very, very interesting. A lot of you will notice that with your kit, you've got little chips on it and firmware, and you've got the ability to change and sort of optimize what the electronics actually do. But very quickly, I think you're all onto the same picture. Um, you needed to understand power management, firstly, in both scenarios very well. And you'll find that the power optimization comes through with how you manage the electronics itself. It's also how you manage the physical world around you. And you'll find that with proper, good power management, you could really, really get, well, firstly, as we saw with Apollo, it could be life-saving, ultimately. So it's a very, very important aspect when you consider what happens in space with these particular types of modules. So very quickly, we're going to have a quick session and we're going to run through various different terms, etc. I'd like to get to a point where I've got a little experiment that I want to show you, particularly around circuits, and just to show you how the physical world really translates to the mathematical world and why mathematics is actually important in this type of thing. But yeah, let's kind of see how quickly we get through this. And again, please feel free to have a conversation with us. We'd like for you to just go ahead and chat, interrupt, ask questions, etc. So firstly, we know that the world around us is made up of various different things, and the things are made up of molecules, and molecules are also made up of atoms. So yeah, a lot of you know that we do understand what happens even at a smaller level than atoms, and some of you might want to look into things like quantum theory and quantum mechanics, etc. But it's just such a massive world, whether you go down to the micro level or even to the macro level when you sort of look at space. But not surprisingly enough, you'll find that looking at a very quick picture here of what an atom looks like, doesn't it remind you of the solar system, right? You've got the sun in the middle and you've got a whole bunch of planets spinning around. So it's almost as if it's a complete carbon copy of what's happening big versus small. But every single material, whether you're looking at a cup, whether you are looking at your laptops right now, whether it is a carpet or your hoodies or your jerseys for that matter, they all are composed of different types of materials, and the different qualities of it, the characteristics of these different types of materials, excuse me, are all determined in terms of its actual molecular and atomic makeup. Okay. So a very quick, I think a lot of you would have covered this in high school already. At the very middle, you've got what's called a nucleus, and you'll find spinning around the nucleus are a whole bunch of electrons. Of course, inside the nucleus itself, you have protons and neutrons, etc. But for the purposes of electrical theory, the thing that we are most concerned about are those free electrons that are basically spinning outside of every atom. So the thing that makes electricity work is the movement of electrons from atoms, right? So as you look at, again, if you look at this particular material, I could tell you just by looking at it that there isn't any free electrons, within this particular atomic structure. However, if you look at something metallic, say, for example, like a piece of aluminum or a copper, I could tell you that absolutely there are tons more free electrons. Free electrons are also known as valence electrons. So if ever you come across the word valence, it talks about, it actually refers back to a free electron. Now, the ability of a particular material being able to conduct electricity or not conduct electricity is stemmed quite deeply in terms, again, of its atomic structure and whether or not there are free electrons there, right? Conductors, if anybody wants to shout out, what is a conductor as opposed to an insulator? I'm just seeing. I'm going to pick on Seth because I can see Seth. Seth, are you able to tell us the difference between a conductor and an insulator? You're on mute, Seth. I'm not sure if anybody else would like to take a stab at it. Okay, so very, very, very quickly, let me help you with that one, Seth. So a conductor has the ability to conduct electricity, whereas an insulator has the ability to not conduct electricity. Now, these are very key, important aspects. So again, if you look at something like a pot or a teapot, okay? A teapot is typically a good conductor of electricity, and we know this because it also has the ability to conduct heat. However, if the entire teapot is completely steel and you boil it and you try to lift it from the top, we all know that that's not a good idea because you will get burnt. In this instance, an insulator becomes a supercritical part of the equation. So an insulator is something that does not conduct heat in that particular instance. So you would grab, for example, a kitchen cloth, around this, it insulates it, and you're able to now then pick that up. Very similarly, from an electrical standpoint, there are certain instances where if you look at your power plugs that power up your laptops, okay, you can safely touch it. Although inside of it, you've got power running from the plug to the laptop charger. So the insulator here again protects you from actually being shocked, just by way of example. So moving on to the different elements of what is electricity is all about, etc. Now, remember, I mentioned to you that electricity is really all about the ability to move electrons from one point to another. Now, typically, if you take a piece of copper, there are free electrons available on it. However, it needs something to push those electrons along. Okay, so think of, for example, you might have a pipe with some water on the inside. And if you just block off the ends, right, that water is not going to go anywhere. Okay, it's just going to continue to stay within the pipe itself. Now, when you apply, for example, a pump, say on the one side, and you sort of pump it through, all of a sudden there's a force that pushes the water through. Okay, that is what is from a voltage perspective, is an electromotive force. Okay, you'll find that voltage is also referred to as potential difference, and you'll see later on with the experiment exactly what is meant by potential difference. So voltage is actually the force that makes the electrons move through. Another thing about the voltage itself is that there are two types of voltages. You can either have AC or you could have DC. Okay, so AC stands for alternating current, and DC stands for direct current. The key difference, I think, for the context of this conversation is that think of direct current as not something. It is basically a voltage that is static, and it doesn't necessarily change polarity. Whereas if you look at an alternating current, you'll find that the polarity, which is typically referred to by a plus or a minus, is constantly varying. There are different sort of applications and why we need why AC and DC exist. But just very quickly to tell you, the reason why AC exists is when we generate power, typically we use something called a generator. Now, if you think of a typical electrical motor and you apply some sort of a propeller at the end of it and you stick it under a flow of water, it will then start to spin. And that propeller is connected to a shaft inside the actual motor itself. The shaft then has a bunch of coils on it, okay? And the coils are surrounded by permanent magnets. Now, as those coils intersect with the different magnetic fields, it starts to generate current. However, the current that is now generated is alternating. But again, you're welcome to share some thoughts in the chat group as to why do you think that it's always alternating within a generator. When we compare that to something like DC, so DC current, for example, is generated by solar panels, right? So a lot of you would have seen these massive black sheets that are typically installed at the top of a roof or even in an open field, okay? And you'll find that we then run those panels into sort of an inverter, and the inverter then charges our batteries. Okay, so the power coming from these solar panels are coming from actually solar cells, and solar cells are essentially direct current. So in that instance, you'll find that you can easily spot a black and a red cable running out of a solar panel, and that's because the black is always negative and the red is always positive. So you have a static sort of link coming out there. I'm seeing a few messages coming through. I'm just being notified, but I can't see those messages. So if you're Grace and Judy, you could tell me if there's any particular questions that pop up. So great. Now that we have the ability to generate power, whether the power is coming through an AC source or it's coming through a DC source, think about, for example, from a solar panel perspective. If during the day you're able to capture power, okay, and you connect it directly to your load, what happens at night? Okay, so it becomes a huge problem because there is no sun at night. There is nothing hitting the solar panels. And what do you then use to power up the rest of your household? This is where batteries come into play. Now, the purpose of batteries is that they're really just an energy storage mechanism. So the whole point of any of these types of systems is that whether you have generated power coming through AC or whether it's coming via DC through solar panels, the idea is to store the collected power into a battery, okay? And that's why you find that almost every system that you interact with that has some sort of generating capability must have some type of battery associated with it, okay? Now, the world of batteries in itself, we could probably spend a complete day talking about the different types of cells or batteries available. So you'll find the actual definition of a battery. A battery is actually a collection of cells, right? A single cell, and you'll see at the bottom there, some of you might recognize that as the symbol for an actual cell. So when we're drawing electrical circuits, you have a long line and a short line, and the long line typically refers to the positive side of the cell, and the short line is typically the negative. However, when you want to show a battery is really a collection of cells. So you might have a long and short, long and short, long and short, sort of cascaded, showing you multiple different cells within a battery. A coin cell, some of you might have seen that, for example, you'll find it in your watch. There are some types of remotes that have their little tiny circular buttons when you sort of look at it, and vary between 1.5 to 3 volts, and well, up to 3.3, I think. Then, of course, you have the other batteries that some of you might have come across. I think some may be referred to as a penlight battery, for example. So those are typically your AAA type batteries. You also have your AA type batteries, and you'll find that there's a whole coding system that talks about a AA, AAA. It even goes on to a C battery. You even have D cells, which are the more larger capacity type batteries. Some other batteries you may have come across is if some of you have things like inverters at home. Lead acid batteries, for example, were mostly quite popular for inverters, but they have now since been replaced with the more efficient lithium ion type batteries. However, cars still continue to make use of lead acid batteries. So there's a whole world of different batteries out there. They have different types of chemistries. They have different types of abilities and storage capabilities and capacities. And therefore, we say that there's a purpose for each and every one of these. Batteries can also be connected in various different ways, right? So, for example, from a series perspective, if you take a 1.5 volt battery and you put that in series with another 1.5 volt battery, it has the ability to give you a 3 volt output. So you start to add all the voltages that you sort of connect up from a series perspective. However, the current that flows through that series configuration remains the same. So you're not necessarily increasing the amount of current that's going to flow through that circuit. Now, when we look at the parallel configuration, that is, if you take a 1.5 battery and you connect it in parallel to the other, and you get another battery and you connect it in parallel, you connect all of the positives together and you connect all of the negatives together. That ultimately gives you a parallel configuration. When you measure the voltage across that setup, the voltage across it will always be so if we're using 1.5 volt batteries, the voltage will always be 1.5 volts. Okay. However, the current capacity in this instance triples. So if we used 3 batteries in parallel, you now have 3 times the amount of current that can be supported within that particular circuit. Okay, so that very quickly was what voltage was all about. We're going to get to a point where we're going to bring all of this together with a very quick experiment explaining to you the different types of elements within the circuit. But this is essentially some of the essential theory that needs to be covered. So again, just make sure if there are any particular questions or comments that anybody would like to make. Just double checking. Great. Okay, so what I should have started out with by saying is typically for an electrical circuit, there are 3 main elements that you really need to be concerned with. Okay, the one we've covered was voltage. The second element now is current. Okay, so current you can think about as, again, if you use the pipe analogy, okay, think of a stream of water that runs through that particular pipe compared to, say, a river, of water sort of flowing through a particular pipe. Compare that to, what you would typically find, say, at a massive waterfall. There's a gush of water flowing through. So you could think about current essentially as the flow of electrons, but the flow rate that these electrons are spinning around in a circuit basically tells you about the amount of current that the circuit is currently supporting. You'll find that electrons, they will have to flow from the positive terminal to a negative terminal. And that's always the case here. The unit, if you can recall, the unit for voltage was the volt, and it was represented by the letter V. In this instance, current is essentially a unit called the ampere, or for short, a lot of us just call it an amp, and it is represented by the letter A. And then, of course, yeah, from a DC versus AC perspective, again, very similarly, you'd find that the flow of current also changes because there's a change of polarity. As we said, with AC constantly changing its polarity, the flow of electricity keeps changing because, as you can see from the top line, electrons will flow from the positive terminal to the negative terminal. So that will always constantly change its direction of flow. Whereas DC, you can expect the flow to continue to be in a single direction. The symbol on a diagram is typically represented by an arrow. So you'd find it could be any type of arrow. It could be an arrow on the outside. It could be an arrow on the line itself. And sometimes it's also represented by the letter I. Okay, so when you see I on an electrical circuit, it is typically referring to the current flowing through it. Okay, the third element that makes up an electrical circuit. Okay, so I mentioned there were three things: the voltage, the current, and now we talk about the resistance. Okay, now again, using the analogy of a pipe, we said that in a pipe, again, with voltage, if you close off the ends, the water is going to just stay there. You need to apply some sort of pump to it. Okay, and that's your battery. Your battery is your electromotive force that will then push the water and get it flowing. Once it is flowing, now moving on to the current, you'll find that there's a stream of current flowing through the electrical circuit. Now, that flow could be, as I said, a little stream, it could be a river, or it could be a gushing waterfall, right? So that tells you the different levels of flow of the current, essentially. The third thing, from a resistance standpoint, here you could think of a resistance being the thickness of the pipe. Okay, so if you find that there's a very small resistance, and in a circuit, or well, in a water circuit for that matter, the flow suddenly becomes very, very constricted, right? So the resistance has the ability to control the flow of the actual current through the electrical circuit. However, if you suddenly open up into a very big pipe, there is no resistance to the flow of the water itself, and the water is able to flow a lot quicker. Okay, so resistance is really all about the opposition to the flow of current. Another way to think about it is think of your tap. I think a tap makes a very good resistor. If we didn't have those types of resistors in play, it'll be very difficult for us to have water coming out of our taps at homes. So typically when you close the tap, it's very, very high resistance. In fact, it's so high that it actually becomes an insulator. Okay, so the water then stops from flowing. But as you open the tap slowly, okay, you're starting to lower the resistance. The water then starts to trickle through until, if you fully open the tap, which means there's almost no resistance, there is a full flow of water coming through. Okay. Now the unit for resistance is the ohm, and you'll find its symbol is the Greek letter omega. Okay. If you look onto a circuit diagram itself, you'll see it's a little squiggly zigzag. You'll see that I've got it there with R1 on top of it. And that's typically how you would find it drawn in an actual circuit itself. So the factors that affect resistance are a range of different things, right? It could be the length of something. So if you take a single piece of copper, for example, over a short distance, it might have a certain amount of very low resistance, but excuse me, as you start to then extend the length of it over kilometers, you'll start to find that the resistance will increase, okay, because it's traveling a much longer distance. If you look at things like area, okay, a very thin piece of copper will actually have a higher resistance as compared to a thicker area of copper, okay? If you look at the types of material, similarly, whether it's copper versus gold versus a string of cotton, the different types of materials will tell you what is the best type of resistance there. Also, from a temperature standpoint as well, you'll find that the resistance is affected. So when we start to increase the temperature of something, the resistance will actually start to increase. When you lower the temperature, the resistance starts to get very, very low as well. So some of you might have come across a term called superconductors. So superconductivity is achieved at very, very, very low temperatures. Okay. So you've seen the little bits and pieces. We've spoken about the battery itself. We've spoken about the resistor. We've spoken about the current itself. But how do we actually build an actual circuit itself? So remember, for electricity to flow, it's got to be a closed loop, right, of all these different types of components, number one. And number two, you've got to have a battery or a cell or what's called an electromotive force, something to push the water along within the circuit itself. So it has to be a closed circuit with some sort of power source that gets current flowing. And this basically is what a standard basic circuit looks like. The other symbol you probably were not aware of is the one at the bottom where it says GND. That is just something called ground. Ground is usually a negative. It connects to all the negative components or the negative elements of components within your circuit. But more specifically, if we apply that to, you'll find a lot of you at your homes, right? You've got these lightning conductors that basically stick up at the top of your roof, and there's a massive metal cable that is physically punched into the ground, okay? So that allows the lightning conductor to catch the lightning before it hits your roof and to then transmit it straight into ground. So it's basically the same sort of concept. Now, we say that a circuit is closed when everything is able to connect and all sort of work and function. We say that the circuit is open if you disconnect the battery or if you disconnect any of these elements from within the circuit. Then if the circuit is open, no electricity will flow and nothing will happen. The other additional component you'll find that I've included here is something called an LED, and I'm going to show you just now what that essentially looks like. But LED stands for light emitting diode. It's that little red light that you see when you turn on your television, or when you press a button on your remote, you'll see this little red light that basically comes on and goes off. So it's a little light ultimately that's used as an indicator. Okay. I'm just going to see if I can cover these laws very quickly. Okay, so Ohm's law and Kirchhoff's law, I'll be covering that just now, but very, very quickly in terms of Ohm's law, I mentioned to you that you need to have three things to basically complete your circuit. You need voltage, you need current, and you need resistance. Now, Ohm's law basically states that the voltage is equal to the product of the current and the resistance. Okay, so it says that the voltage drop across any particular component is equal to the current flowing through that component multiplied by the resistance of that component, or V is equal to I times R. Okay. But we will get to that just now. And I'll also tell you a little bit about another law called Kirchhoff's law. Okay. Great. So from a UN SDGs perspective, I know in this course, we have this covered in practically all the various different sessions. So this particular course is very much aligned with UN SDG number 7, which relates to affordable and clean energy. Okay, so there are different types of energy sources, but it's just important for you to know that there are alternatives and clean alternatives to the typical oil and coal type of non-renewable type energy sources. A lot of you would have seen biomass, for example. If you're living along the coast, there might be elements of wave technologies where they use the motion of waves to generate power. I'm pretty certain that all of you understand exactly what solar is all about. From a water perspective, a lot of you would be familiar with the term called hydroelectricity, and that's how a lot of our power really is generated through power. There's geothermal, and then of course there is wind. I'm pretty certain that a lot of you would have seen these massive, big machines with big propellers spinning around constantly, catching the wind and converting that into power. The great thing about the difference between renewable and non-renewable means that it's coming from a finite source, right? Whereas renewable simply means that we've got infinite access to the energy, and therefore it is fully recyclable. Okay. So from a power generation perspective, so the main element, I guess, that you need to understand from these various different pictures is that we spoke about a generator, right? And a generator is essentially something that converts physical motion to electricity, okay? And typically it is doing that. It takes some physical motion and converts it to alternating current, okay? Now, in the example here on the top, you'll find that typically before the generator, you have some sort of turbine, right? Or if you look at nuclear energy, just by way of example, nuclear energy has, you have a whole bunch of different rods, and these rods generate heat. The heat then heats a massive amount of water. And the water then at high temperatures become vapor. And then water vapor, if you think back to days of the steam engine, right? It then drives a turbine, which then drives the generator and then generates power from that, essentially. So that's essentially the source of the power and how it is generated. Now remember that once the power is generated at a particular point, let's say, for example, it's now generated somewhere in Nairobi. It then has to be distributed through to Nakuru. It then has to go through to Mombasa, or it's got to then find its way into Kigali. It's got to then find its way up through to Lagos. So how do we get the power from one point to another point? The diagram at the bottom basically shows that firstly, power goes through transmission lines over very, very long distances. And then, of course, they go into different phases where they then step down the power to eventually reach you at the home, right? So it's generated, it's then distributed, and then passed on to the home environment. Very similarly, from the aspect that I spoke to just now was AC. From a DC perspective, you now have a solar panel array that's collecting photons coming from the sun. And that then converts photons into electricity. That then feeds into a charge controller. And remember, I mentioned to you that the idea is we need to store the power that's coming from the sun. And the place that is stored is actually within the battery. So there's a whole bunch of batteries at the bottom. We then take the DC voltage that goes from the batteries into an inverter. And an inverter basically takes the battery power DC and it converts it to AC. And the reason we do that is in a typical household environment, most of the things we've got around require AC. So we might have a fan, we might have a microwave oven, we might have a fridge, we might have a television. A lot of these appliances come standard, with an AC plug. So therefore, we require this inverter to do the conversion for us from one to the other. Okay. Now I think we are getting to. Okay, so I think at this point, I'm just looking at the time as well. I'm going to quickly jump to the experiment, which will summarize the next couple of slides for us. So I'm going to quickly stop that share and let's see if I can change cameras and let's hope that this works for us.
That's great. Yeah, we have around about 10 minutes left, Collin, if that's okay.
Cool. Okay, excellent. Let's just do that. Okay. And I think I need to turn off the background. Okay, great. So
great, we can see that, yes.
Okay, excellent. That works. All right. So I think this is really the crux of the talk today. So it really covers up quite nicely. So what I've got going on here, this is called a breadboard. A breadboard is really something that we build and test. A whole bunch of electrical circuits. Now, if you recall, the one thing that we do need in an electrical circuit is power. So I've got power coming in on this red and black, which is my battery pack. And my battery pack is essentially, it's basically getting 5 volts delivered to the circuit. Okay. Let's just quickly turn it on. And the fact that you're seeing that little red light will turn on, we now know that there's electricity flowing within the circuit. Okay, so we've got power coming into the positive. It's going across this component here, which is the resistor. Okay, resistors are very tiny, and you typically can identify them. They have 3, 4, sometimes 5 bands of color on them, and that is a color code to tell you how many ohms they are. Then that flows through this LED, and it flows back out through the negative side. So this is what we would call the closed circuit. If I disconnect one point that connects all of these things together, it goes off. Okay, that's now opening the circuit. Okay, put it back in again, it becomes closed. So this tool is, let's just bring it back here. This tool is essentially what's called a multimeter. And the multimeter is going to help us to measure things like, here you can see voltage, V. Here you can see the omega symbol, which is your resistance. And here you can see A, which is basically current. Okay, so we've got V, I, and R. So the 3 elements that are required. Now let's quickly check. What voltage am I getting from the battery? If I go there and there, I'm not sure if you can see that, but it's showing 5. Okay, so it might be inverted for, obviously because it's a camera. So we are getting 5 volts. That is, you could think of it as the battery that's connected to this. However, interestingly enough, if we measure the voltage drop across the resistor, let's go here. Right, suddenly we're looking at 3.18 volts that's dropped across the resistor. And let's measure across the LED. The LED has about 1.8 volts. Okay, so one of the Kirchhoff's laws to remember, right, is that the voltage in a closed loop should always be equal, right? So we've got 5 volts coming in. We measured the voltage across here, which was about 3.2 volts, as you saw. And then we measured the voltage across the LED, and we got 1.8 volts. If my maths is sort of more or less correct, that should add up to 5 volts. Okay. So essentially, that just shows you that, firstly, that particular law is valid. The second bit is, how do we measure current through a circuit? Now, we can't measure current across any particular component. It's got to be in series with something. So I'm going to quickly turn this around to around about there. Disconnect the circuit so I can access those leads. And let's just quickly measure. So when I connect the multimeter, it should turn on the LED and also give me a reading. There we go. I'm recording 6.7 milliamps that are basically flowing into the circuit. So very, very quickly, 6.7 milliamps flowing through the circuit. If you take that and you multiply it by 470 ohms, so 470 ohms is the value of this particular resistor, you should get something around about 3.2 volts. Okay, so that is basically the link between the mathematics and the actual circuit itself. So you'll find that for the assignments and the questions that are sort of coming up, I think that should gear you up quite nicely to answer that question. I'm going to quickly go to this camera and let's just quickly get that in place. Great, and jump to the presentation. Okay, great. So Ohm's law, as we basically spoke about just now, is that V is equal to I times R. So the current flowing through the circuit multiplied by the resistance will actually give you the voltage across it. And we basically tested, as we saw, we tested the various different, we've tested the current and we tested the voltage. And we tested the resistance and we're able to calculate the voltage. That calculated voltage matched up with what we actually saw from a voltage perspective. The other equation that you kind of need to know here as well is the power calculation, and power is equal to the current times the voltage. Now you can start to substitute and rearrange all of these different elements as you please, but this ultimately is the basic law that you need to understand from electrical theory. Okay. Kirchhoff's law, we spoke about, all the voltages around a circuit would typically add up. So we said the voltage drop across the resistor was 3.2 volts. The voltage drop across the LED was about 1.8 volts. Add those up, it can't give you 5 volts. And we know that the power coming, or the voltage coming into the circuit was 5 volts. So we know that that definitely works. There's also a Kirchhoff's law from a current perspective, which basically says that all the currents flowing into a point will equal to all the currents leaving a point. Okay. Don't really need to remember that too much just now, but just know that it exists. We've completed that experiment. Just very quickly to wrap up, on the satellite side, how is this stuff applied from a satellite perspective? This is how we power satellites. Remember, these are expensive communications equipment. They are scientific instruments. They have telescopes on them. They have sensors, etc., and they all need to be powered. Where do we get the power? We get it from the sun, right? The fact that they have direct visibility of the sun. And you'll find that here, for example, is a body-mounted solar array. And then, of course, you've got your sun tracking type solar arrays, which also spread out. And they essentially capture the sun's rays, convert that into a DC voltage. Remember that these satellites would also need to have batteries to store the power, and then, of course, continue to feed the various different electronics. Again, you all have been through the series and the parallel bit. The same concept applies. If you sort of connect two solar arrays in series, it will continue to have the individual voltages added up, but the current will continue to be the same. However, if you connect the two arrays in parallel, the voltage coming out of the arrays would be the same. However, the amount of current would certainly increase. And there are many different configuration where methods of changing voltage or current. So you'll find that, by design, your kit comes in little blocks like these, little modules, and it allows you the ability to move them around in different sort of configurations. And the reason behind it is that we need it to be redundant, and it allows you to also fit within the specific physical space. Okay, the kit. Yeah, and I guess from a last comment perspective, there is an assignment and a whole bunch of questions, I believe, Judy, that have already been loaded onto Canva, which you are encouraged to go ahead and answer it. And you'll find that all of the equations that you require to answer these questions are within this presentation. You should not really have too much of an issue there. But yeah, I'm not sure if you have any time to maybe have a quick conversation around, a Mars habitat. What would be required to make your stay on Mars comfortable? And how would you maintain that comfort level?
Yeah, Colin, I think that is really important because yes, the mega assignment is, design considerations for a habitat on Mars. So yes, certainly, let's discuss that. I think that'll be really important.
Right, excellent. I'm just wondering if there's anybody that would like to kick us off with any comments around a habitat in space, and what would be some of the things. Let's start with, what are the things that we require as humans to survive in space? We have Amy Kun. Okay, if you could go ahead and tell us what you need.
Human beings need oxygen.
Excellent. Right, we absolutely need oxygen to breathe. What else do humans need? Think about that Apollo 13 disaster or incident. There are some clues in there.
Colin, we have some comments also in the Paula's saying, food and shelter.
Yes.
And then
Yes.
I think Josh has come in with, and we need warm climate, warm conditions. It needs to be comfortable, technically comfortable, not too cold and not too hot. Otherwise, our cells start to break down.
Yeah, absolutely. If you look at Judy, for example, she's got a scarf on. If you look at my side, I've got my hoodie, right? We're desperately trying to keep warm in this cold weather of ours. So can you just imagine when you're up in space, you definitely are going to be cold. So you need some sort of heating element. I like Godwin, you obviously good health. All of these elements are connected together. So we need heat, we need oxygen, we need to manage our health. So all of these things have elements of, yes, I like what A.V. Bennett or Av Bennett, a suit that can withstand solar radiation, a habitat that can block harmful UV light. You want to be comfortable when you're out in Mars. You want to have a decent night sleep. You want it to be comfortable, warm. You want to have air that you can breathe. Potentially, some of you might even want to stream some Netflix, or you'd want some sort of entertainment. Or you might read a book, but you'll need some lighting. Okay. You might want to communicate with somebody potentially on the other side of the planet, or even on the other side, back to Earth, at least. On that point, you'll find that if you attend next week, where we talk about connectivity and communications, There's some really, really cool stuff that we'll talk about in terms of what Elon Musk, for example, is doing with interplanetary communications. We're seeing clothes, that are required. So a lot of these different elements to keep us safe and alive in space, we need power, right? We absolutely need, firstly, how do you power up, the machines that are going to be generating oxygen? I think they're called MOXIEs, Judy. So there is an ability to generate oxygen.
MOXIE. Yes. Yes, a MOXIE process. There's two types. The one is when you take carbon dioxide and you actually split that to recover the oxygen. But also what you can do is that you can also split water into oxygen and hydrogen. And yes, solar panels are really great for that, because what you need is you need you need to be able to store that energy. And the great thing about solar panels is that you harvest the energy, you store it in batteries, and then you reuse it after that. So yes, absolutely.
Absolutely spot on. So most elements that we require to maintain human life, also to maintain our comfort levels. Remember, we need a certain temperature to be comfortable, right? We need a certain quality type of air to be comfortable. So all of these different aspects require power. And of course, the best way to get power would be solar panels up into space. So maybe just for all of you to think about is, what are some other ways that you could potentially generate water while on Mars? And maybe some aspects of that you could use in your mega assignment. But I guess, that was a fairly quick flyover through power. If you have any further comments or questions, let's interact beyond today on Canva itself. But I guess with that, from my side, it's thanks very much for being attentive, and I guess it's over to you, Judy.
Great. Collin, thank you very much. Grace, would you like to wrap up? How about that?
All right. Thank you very much, Collin, for today. It's always great hearing you. And yes, thank you very much. And thank you, everybody. I am so happy with the assignments that I've got so far, and the amount of assignments that I have got and grading. I'm really happy grading, and I hope that we will all stay excited and we'll all have fun through the program. And if you do have any question, if you do need help, please do not hesitate to just write something on the discussion section, and we'll always come back to you. And thank you so much, Judy, for your support as well. We really appreciate you. And have a good evening, everybody.
Great. Thank you, Grace. Thank you so much. And Collin, yes, we're using the discussion section a lot. So we may receive some questions during this week on the assignment. So regarding power, there's two assignments, and then there's one quiz. And I've also made available the assignments and the quiz for your session next week, Collin, which is on connectivity and communication. So if any of you want to start tackling that in the meantime, yes, why not give it a try? So that's absolutely wonderful. Collin, once again, thank you so much. I always learn so much, because, over the years, one forgets these things. Thank you so much. And we look forward to next week, time with you again.
Excellent. It's my pleasure.